Let us continue our discussion on linear block codes and simple parity check. A linear block code is a special type of block code with an interesting property. The XOR sum of any two valid code words results in another valid code word. This property makes them very easy to work with in hardware. The simplest example is the simple parity check code. Here we add a single redundant bit, the parity bit, to a data word. The value of this bit is chosen to make the total number of ones either even or odd based upon the agreement between the sender and receiver. This allows for basic error detection. So in simple parity check code, the data word is assumed of k bit. Then the k bit data word is encoded into an n bit code word by adding one redundant bit. So n equal to k plus 1. This extra bit is called the parity bit. The minimum Hamming distance for this category, the minimum Hamming distance is 2. This means it is a single bit error detecting code. It can correct any error. Now let us see the specific logic used by the sender and receiver for simple parity check. The encoder for a simple parity check just calculates the number of ones in the data word. If it is odd, it adds a 1 as the parity bit to make the count even. If it is even, it adds a 0 to keep the number of ones even. At the decoder simply counts the ones in the received code word. If the count is odd, it knows an error has occurred. However, this code has a major limitation. It can detect only an odd number of errors. For example, if two bits are flipped, the parity will remain correct and the error will go undetected. This gives it a minimum Hamming distance of just 2. Simple parity check codes are effective for detecting single bit errors. They cannot correct errors nor can they detect an even number of errors. Next is the Hamming code. Hamming codes are a more powerful error correcting technique. So you can correct a single bit error. To overcome the limitations of simple parity, we turn to Hamming codes, which are specially designed for single bit error correction. This is made possible by placing the redundant bits at positions that are powers of 2. For example, the positions 2 raised to 0, 1, 2 raised to 1, 2, 2 raised to 2, 4, 2 raised to 3, 8, and so on are the positions that are reserved for parity. The value of each redundant bit is determined by a parity check on a unique set of other bits in the code word. This clever bit placement strategy is what helps the Hamming code detect errors and correct them. So we choose an integer m greater than or equal to 3 to allow error correction because the number of error bits can be that can be corrected is 1 if given the size of the data word is at least 3. So the value of n and k, the data, n is the code word length and k is the data word length, are calculated from the m. N equal to 2 raised to m minus 1 and k equal to n minus m. The number of check bits or the redundant bits is equal to m. For example, if m equal to 3, then the code word will be of length 7 up to 7 and the data word can have 4 bits in it. This results in a Hamming code of a combination C of 7 comma 4. 7 represents the length of the code word and 4 represents the length of the data word. The minimum Hamming distance for this combination is 3. So for such Hamming codes, 1 bit errors can be corrected, and the minimum distance between any two code words is at least 3. So here you can see the bit positions that are reserved for parity. The first position, second position, and the fourth position are reserved for parity. The remaining positions can be occupied by the data bits. The Venn diagram shows you the parity bits, the influence of data bits on the parity bits. For example, A0, A3, and A1 will influence R0. Similarly, R1 will be influenced by A0, A3, and A2. R2 will be influenced by A1, A2, and A3. We will summarize the encoder, decoder, and also look at the performance characteristics of Hamming codes. The decoder performs a series of parity checks on the received code word. If any of these checks fails, the resulting combination of zeros and ones forms a binary number called a syndrome. This syndrome directly indicates the exact bit position of the error. This allows the decoder to flip that single bit and correct the data. So because of this, Hamming codes have a minimum Hamming distance of 3. This means they can correct any single bit error. Additionally, they can also detect any double bit error even if they can't correct it. So a standard Hamming code can correct a single bit error or detect a double error. To detect burst errors of size n, the frame can be split into n code words. By arranging code words in a table and sending bits column by column, a burst error of size n will corrupt only one bit from each code word, allowing for single error correction on each. Now we'll explore cyclic redundancy check or cyclic codes. Cyclic codes are special linear block codes with an additional property. If a code word is cyclically shifted or rotated, the result is another valid code word. For example, if 10110000 is a code word, valid code word, then upon left shift, the code word becomes 011001. The most significant bit will become the least significant bit now. And the resultant code word is again valid. So it is a valid code word. CRCs are widely used category of cyclic codes, especially in networks like LANs and WANs. They are primarily used for error detection. However, uh, they cannot detect and correct errors. They can only detect errors. They cannot correct it. CRC codes are based on polynomial arithmetic. It offers exceptional error detection capabilities using the polynomial arithmetic. We will see one example of CRC. The CRC mechanism is elegant. At the sender, the data to be transmitted is treated as a polynomial. It is divided by a pre-agreed upon binary number called the generator polynomial or the divisor. The remainder of this division is the CRC checksum. The sender then appends this checksum to the original data and transmits the entire unit. At the receiver, the entire received frame is again divided by the same generator polynomial. If the remainder is a 0, the data is assumed to be correct. If not, it detects an error and rejects it. You can see an example here. Assuming the data word is 1001 with 4 bits in it, and a divisor 1011. Usually divisors are prime numbers. So here 1011 represents 11 in decimal. 11 is a prime number. The first step is to augment the data word with uh, n minus 1 zeros, assuming n is the size of the divisor. So number of bits in the divisor minus 1 are the number of zeros that have to be augmented to the data word, because we are expecting a 3-digit remainder from a 4-digit divisor. So now performing the division, we can just perform the modulo 2 division. We are actually not interested in the quotient. Uh, you can simply perform the XOR operation on the bits from the dividend with the divisor, and then the resultant bits will be noted down. Then you perform the XOR operation again to see the remainder. So you have to repeat the process until you see uh, a maximum of 3 digits in the remainder. Then the data word along with the remainder will be sent to the receiver. The receiver performs the modulo 2 division using the same divisor, and then checks whether the remainder is a 0 or not. If the remainder is a 0, then it will be accepted, otherwise it will be rejected. Modulo 2 division involves XOR and not subtraction with borrows. If the leftmost bit of the current dividend segment is a 0, all zeros divisor is used. Now let us look into the polynomial representation of data in much more detail. To understand why CRC works so well, we think of the binary bit stream as a polynomial. For instance, the bit string 1011 can be represented as a polynomial x power 3 plus x power 1 plus 1. The generated polynomial is chosen carefully to have specific mathematical properties. This polynomial approach allows CRC to detect all single bit errors. It also detects all burst errors that are shorter than the degree of the generator polynomial. It also has an extremely high probability of detecting long burst errors. This combination of power and simplicity is why CRC is a standard in so many protocols. Next, we'll define checksum and one's complement arithmetic it relies on. Another simple error detection technique is the checksum. This method involves dividing the data into fixed size frames. All of these segments are then added together. The sum is then complemented to get the checksum. Checksum is appended to the data and then will be transmitted. The arithmetic here we use is the ones complement, where you simply invert all the bits of a number. This is a form of modular arithmetic. In this process, any carry that overflows from the most significant bit is wrapped around, and it will be added back to the least significant bit position. So assuming that the data stream involves multiple integers 7, 11, 12, 0, 6 and minus 36. Receiver adds all numbers received including the checksum. If the result is a 0, no error, otherwise it detects an error. If a number has more than n bits, the extra leftmost bits are again added to the n rightmost bits. A negative number is represented by inverting all bits of its positive counterpart, which is the ones complement. This is equivalent to subtracting the number from 2 raised to n minus 1, given n is the number of bits. You can see an example here. 6 in binary is represented as 0110, and negative 6 is represented as 1001. We invert zeros and ones. So let us see the full process of checksum at both the sender and receiver. The sender divides the data into 16-bit segments, ideally. It then computes the sum of all segments using ones complement arithmetic, and then takes the ones complement of this sum to create the checksum. The checksum is then appended to the data and sent. At the receiver, the entire received data, including the checksum, is added up. If the final sum is all ones, which is the ones complement of 0, the data is considered valid, otherwise it is rejected. This checksum is widely used in Internet Protocol IP and User Datagram Protocol UDP. It provides basic level of error detection. So now let us see the three distinct types of services offered by the data link layer. The data link layer does not just provide a single service, it offers a range of options to the layer above it, the network layer. Each option has different trade-offs in terms of reliability and overhead. We can think of these as a spectrum from the least complex to the most complex. Unacknowledged connectionless service, acknowledged connectionless service, and acknowledged connection oriented service. Unacknowledged connectionless service doesn't involve any error recovery, so no mechanisms to recover lost or corrupted frames at this layer. The source machine sends independent frames to the destination machine without requiring acknowledgements. Examples are Ethernet, voice over IP, where real-time operation is prioritized over quality. Next is the acknowledged connectionless service. We have two types of acknowledged connectionless services. Acknowledged connectionless service still does not establish a formal connection between the sender and receiver. However, the sender will wait for an acknowledgement for each frame. If a confirmation is not received within a set timer, the frame is retransmitted. This adds a basic level of reliability for scenarios where establishing a full connection is uh, computationally or costly. The most robust option is the connection oriented service. Here, a formal connection is established and maintained. Every frame is numbered. This service guarantees that data will arrive in the correct order without duplicates or missing frames. This provides the highest degree of reliability. Next are some elementary data link layer protocols designed for an ideal noiseless channel. So these protocols assume a perfect noise-free channel where data is never corrupted or lost. The simplest protocol is a one-way transfer with no flow control. We then add a single layer of complexity with the stop and wait protocol, which incorporates flow control by having the sender pause for an acknowledgement before transmitting the next frame. So these protocols are foundational models. They help us understand the basic principles before we add the complexities of real world, the noisy channels. So now let us see the stop and wait ARQ protocol. Finally, we bring all our concepts together with the stop and wait ARQ, designed for a noisy channel where frames may be lost or corrupted. The sender transmits a numbered frame and starts a timer. If the receiver gets a corrupted frame, it simply discards it, and then the sender's timer expires without an acknowledgement. It assumes the frame was lost and then retransmits the frame. The use of sequence numbers is important to identify the packets which are delivered correctly and which are not. It prevents the receiver from processing a duplicate frame that might have been sent due to a delayed acknowledgement. This simple protocol elegantly combines flow and error control to provide a basic but reliable data link service. While the stop and wait protocol introduces flow control, noiseless channels are not existent in reality. So stop and wait ARQ adds a simple error control mechanism to the stop and wait protocol. If the receiver receives a corrupted frame, the receiver silently discards it. Error detection is inferred by the receiver's silence. The sender keeps a copy of the last transmitted frame. A timer is started when a frame is sent. If the timer expires without an acknowledgement, the frame is resent, the copy is held, and the timer restarts. With duplicates and out of order frames, because of the uh, frames are numbered using sequence numbers, the receiver uses the sequence numbers to distinguish between original and duplicate frames and to detect out of order delivery. Acknowledgement frames also carry acknowledgement numbers, which announce the sequence number of the next frame expected by the receiver. The sender discards corrupted acknowledgement frames or ignores out of order ones. You can see an example flow of lost frame or acknowledgement. The sender starts transmitting the frame 0, which is acknowledged, and then frame 1 is lost. Then it times out because the frame is lost, the receiver cannot acknowledge it. So the timer will expire and will retransmit the first frame again, frame 1. Now frame 1 is successfully delivered and will receive an acknowledgement. Then it transmits the frame 0 again. The receiver acknowledges the frame 1 by sending an acknowledgement 1, but acknowledgement 1 is lost. Then again the timer for the frame 0 expires. So the sender starts transmitting the frame 0 again with a timer restart, and now the frame is arrived successfully. Because this was a duplicate frame that was already delivered, the acknowledgement will be sent. Still, even if it is a duplicate frame, the frame will be discarded, but the acknowledgement will be sent back to the sender. Upon receiving the acknowledgement, the sender will advance the window to the next packet in the sequence. So small variant of this stop and wait protocol is go back and ARQ. This protocol operates on two primary components, a sliding window at the sender and a simple buffer at the receiver. The sender's window defines the maximum number of unacknowledged packets that can be in transit. The receiver, in contrast, maintains a strict order, only accepting packets that arrive in the correct sequence. Any packet received out of order will be discarded at the receiver's response. Will be a cumulative acknowledgement confirming the last packet received in the correct sequence. If a timeout occurs before an acknowledgement is received, the sender assumes the packet has been lost and initiates a retransmission of that packet and all subsequent packets in its window. The sender processes all the acknowledgements, advancing its window to include all delivered packets. The transfer will continue till all the packets are successfully delivered. Thank you.